The next topic, the topic we're going to be covering today, deals with Android concurrency and synchronization. And we are going to have a whole pile of parts in the module here that's going to talk about different aspects of concurrency and synchronization. I'm going to start out first by giving some of the motivation for using concurrency. Why would you want to use it? What are some of the things that make it tricky? And we're going to see that concurrent software can simultaneously run multiple computations that may interact with each other. The may is important there. Sometimes they do, sometimes they don't. And we'll see when we talk later about synchronization that when the concurrent computations interact, then you have to understand synchronization and even perhaps scheduling in order to make sure that your concurrent operations don't stomp all over each other. And we'll look at lots of examples to help make that point more clear. We're also going to talk about the mechanisms that Android provides that allow you to be able to manage multiple threads that run concurrently within a process. And you'll see that in addition to having threads run concurrently within a process, in later modules in the course, we'll talk about communicating between processes using various inter-process communication mechanisms. The first go-around here for this discussion, we're going to assume, for sake of simplicity, that everything runs in the context of one process. But that's very easy to change as we get into the more advanced features of Android. You'll see that some of the mechanisms for concurrency that Android provides are based on the same kind of thing you'd find in standard Java. So the standard threading and synchronization mechanisms that you find in regular Java for your desktop or server, Android supports the bulk of those. Not everything, but quite a few of them. And you'll also find, and this is not something we'll get to right away, but you'll get to it later, and it's crucially important to do your programming assignment, you'll also find out that there's a bunch of different mechanisms that Android provides that are very specialized for particular idioms of Android programming, particularly things having to do with dealing with the user interface thread not being able to have certain operations called outside the context of the user interface thread. So there's certain things that are specific to Android or more specific to Android that you might not find if you were running in a purely server environment or a cloud programming environment. OK, so let's go ahead and start talking about the first section here. So what we're going to do here is understand the motivations for and challenges of concurrency and concurrent software. So why do people use concurrency? Well, there's a bunch of different reasons. We're going to look at 4 reasons, some of which were really important historically, some of which are becoming more important because of certain advances that have taken place with modern hardware and software and different layers of software. So one of the key characteristics is that it's getting more and more difficult these days to find hardware that's not got multiple processors or multiple cores in it. The modern generation of smartphones increasingly have quad-core processors. There's a whole website that's devoted to telling you all there is to know about quad-core processors running on Android, which is kind of cool, or quad-core processors running Android. And by and large, almost all modern operating systems support multi-threading, so you can actually take advantage of all those cores. And modern virtual machines, like the Dalvik virtual machine or the Java virtual machine, also takes advantage of multiple cores. And modern middleware, which are the layers that live on top of the virtual machine, also take advantage of multiple cores in various kinds of things that they do as well. So right now, it's very pervasive. It's hard not to get away from it. And so you've got to be fluent with it because you're going to run across it. Another motivation, of course, is as the Herb Sutter, the Microsoft distinguished engineer who has done a lot of work with C++, likes to note, there's no free lunch anymore. Processors, Moore's law, are not getting faster. They're not getting more transistors on a chip at an alarming rate the way they were for decades. They're getting more cores. And so if you don't know how to take advantage of those cores, you're not going to be able to leverage advances in modern hardware. So that's kind of the, if you build it, they will come perspective. There's another perspective as well, which is that the way in which we develop software in the absence of concurrency can actually make your program very convoluted. Now, at first glance, that seems a little bit odd, because one of the things you'll learn very quickly when you start to play with concurrency is if you're not careful, you can write code that's extremely hard to understand, because there's multiple things happening simultaneously. And most human being brains don't deal with concurrency very well, unfortunately. It takes a lot of experience, and sometimes you just got to sit down there and a pencil and paper and draw it out, or crack open your debugger or other find various problems in your concurrent code. But the absence of concurrency is actually complicated as well. And I'll give some examples of this to make this more clear. But if you go back and look at the early days of computing, if you look at the early windowing systems like X Windows, you look at early windowing systems like Microsoft Windows, the early versions of Microsoft Windows, or the various Macintosh-related early windowing systems, they were all single-threaded. And what that meant was that you could not perform blocking operations in your one thread of control, because if your blocking operation blocked, everybody else, not just in your window, but all the other windows in the system and everything going on in the background also came to a screeching halt, at least in systems that didn't support multiple processes, like early Windows did not. And what that meant was that you had a very complicated application programming job often, because you had to decouple the flow of control of operations in time and space. What the heck does that mean? What that means is, if you're trying to do an operation like read to a file, or read from a file, write to a file, read from a network, read or write to a database, grab a lock, anything that's going to require blocking, you couldn't block. Instead, you had to use event-based processing. And that meant you would have to start an operation that ran in a non-blocking mode, go back and handle other things in your main event loop, and then when that non-blocking operation completed, you would get notified somehow, pick up the result, figure out where you'd left off before, and keep running. Now, having said that, it turns out that there's some really powerful patterns for non-blocking or asynchronous programming. Things like proactor, asynchronous completion token, half sync, half async, some of which we'll talk about later in the course, some of which we won't. But the point is that those are even more complicated for most beginners to get their head around. So one of the things that you can do with threading is you can let things block, and the programming becomes simpler from one point of view if you're careful in how you structure your code, because you just make blocking calls just like you do anything else in a non-multi-threaded program. And it looks very much like you're doing standalone programming. So let's take a look and see how this might work. So modern multi-threaded architectures support blocking I/O in certain contexts. And in the case of Android, these are contexts for things that can run, quote, in the background, in threads of control that have been spawned and run doing other kinds of things. So as you'll see when you do your next assignment, we're going to work on the runnables and handlers model of concurrency, which works this way. We're going to work with the messages and handlers approach. We're going to work with async task. All of these things allow background operations to run concurrently, and they can do blocking operations without affecting the main thread of control. Here's a very simple example. If you take a look at the Android documentation on the web, you'll find some elaboration of this point in more detail. And some of your programs will look a bit like this, although not quite exactly the same. So here's an example where we want to use multi-threading to download an image and display it in our browser. So as you can see here, here's a little bit of code. Here we have the set onClick listener method, which we're going to use to create a new onClick listener. And here we have an anonymous inner class, which is going to have the onClick method, which is going to get called back when you click on that particular button. And if you take a look at this code, you'll notice that all this code it looks synchronous in its nature, right? You look like you're going to go ahead and click a button, which is what you do when you click the button on the display. That will go ahead and start a new thread of control. And inside that thread of control, it's going to go ahead and run the run hook method, which you can see here. And the run hook method will synchronously block downloading an image at a particular URL, which you conceivably would have given through other means here. And once that image has been downloaded synchronously, we're then going to go ahead and we're going to post a new runnable to the main user interface thread of control, where when its run method is called, it will go ahead and set the image bitmap to the bitmap, which will then be displayed. So that's a nice example of synchronous communication or synchronous blocking, and then it uses some other magic taking place behind the scenes to handle the various interactions between the background thread and the foreground user interface thread. Any questions about this? You see this particular type of idiom used very frequently in Android. And it's very simple to program. There are some downsides, which we'll talk about later when we start talking in more detail about how this stuff works under the hood and what the different options are from a programming point of view. But it's a pretty good idiom to understand. OK. Another motivation for concurrency and multi-threading is to be able to improve performance. And the basic idea there is we've got all these quad-core processors or multi-core processors, maybe even more than quad-core in a desktop or server machine, and we'd like to find a way to actually take advantage of them. So we want to be able to have multiple things going all at the same time. So you can parallelize communication, you can parallelize computation, you don't have to always sit there and wait for something to happen in a serial way. You can take maximal advantage of the hardware. Now, that only works if you have algorithms that actually have opportunities for concurrency built into them. If you were trying to solve a problem that is inherently sequential, then having a 1,000-core machine won't do a whole lot of good for you. So this, of course, motivates knowledge of parallelized algorithms. There's a wide body of literature now on parallelizable algorithms. There's a wide set of libraries that are part of Java and other languages that help you to implement those kinds of algorithms. So in that environment, you can really get a full speed up. There's something you should probably know called Amdahl's law, which basically says that you can only get benefits from parallelization to the extent to which you can parallelize your code. Kind of an obvious thing to say, but a lot of times people think that if you just throw processors at the problem, things will get faster. In fact, oftentimes when you throw more processors at a problem, at first things get slower because most people aren't very good at optimizing their concurrent programs. So you'll end up putting so many locking operations in your code that even though you have multiple threads, it actually doesn't make much of a difference from the point of view of performance. So then that, again, is where knowledge of patterns really pays off in algorithms. Even in situations where you may not have more than one thread of or more than one processor or one core, there still can be a benefit to having multi-threaded operations. And that becomes obvious if there's situations where you can overlap computation and communication, so that even though something is blocked, you may be able to continue to do work either for real or synthetic. So let me give you some examples. If you've ever worked in a single-threaded environment, you know that when you do a long-running operation, you'll get that annoying little hourglass that pops up. Older versions of Mac were that way, older versions of Windows were that way, and that basically means you can't do anything to the user interface because something else is taking a long time to run, and it's stealing the focus or stealing the thread of control, the focus of control from the user interface thread. So even if things don't actually get done any faster, you get this perception, which is somewhat annoying, that you're being locked out and prevented from doing things. If you've ever used an automatic teller machine, they do all kinds of little tricks there to try to hide this from you. So when you go ahead and put your card in, and you type in your PIN, and then they lead you through a series of menus to withdraw money or deposit money, the user interface is still chunking away, giving you some responsiveness, even though there's probably some kind of database call being made across a network to validate whether you typed your PIN in correctly or whether your card is lost or stolen, and therefore they want to lock it out, and so on. So they use that opportunity to kind of lead you through a set of menus to sort of slow you down a little bit while that other computation takes place in the background. So it gives you this perception that things are taking are more responsive, even though it may not run any faster because there may only be one CPU going on there. Okay, so any questions about the motivations for concurrency? Those are 4 good reasons. These kinds of things tend to show up on quizzes, so it's probably important to understand why they're there. But there's complexities with using concurrency. So one of the things you have to be very careful about when you're first exposed to this paradigm is that you don't let the excitement of trying new mechanisms blind you to all the problems, the traps and pitfalls that will plague you if you don't know how to use them effectively. It's just like anything else. You give someone who's not trained in something very powerful, and they can make a big mess in a hurry. Now, some of the complexities that you run across when you deal with concurrent programming stem from so-called accidental complexities. These are limitations with techniques and tools that we use to do the kinds of work that we commonly are called upon to do as software developers. Sometimes these are things we as developers have very little choice in. We're handed a set of tools. We can't do much about it. Other times people actually make the choices themselves. They may choose to use the wrong tools, and therefore the blame is on them, or the wrong languages. So let's take a look at an example. Historically, people who were writing concurrent programs had to use, by the nature of the languages and the system libraries and frameworks that they had at their disposal, they were forced to use very low-level interfaces, application programming interfaces, which were tedious, error-prone, and non-portable. So it just wasted a lot of people's time. Let me give you some examples of this. So here's an example of a program written in C using POSIX pthreads, which is a portable, at least to POSIX platforms, way of writing threaded applications. So let's take a look at how this works. There's a lot of very error-prone things in this code. One of the things is when you use pthreads, you have to pass a pointer to a function. So here's an example. We're passing print hello world, which is a function, to the code. And it's really easy to make mistakes here. We also have to cast the parameters to void, and we have to make sure that we don't end up in a situation where this thread might run longer than the main thread, in which case the parameters would go out of scope and be destroyed or otherwise get reused. The memory might get recycled somehow. So those are other examples of error proneness in this environment. When we get the parameter to the function, we have to cast it back from void to whatever we think it might be. And in a language like C that lacks runtime type checking by default, you can build it in there, but it's an added capability you'd have to write yourself or use a library to do. We're not really quite sure what we've got at this point. We're keeping our fingers crossed that we've got the right data, but we don't know for sure. And then there's also the use in languages like C of these quasi-typed handles, which are typically either integers or void pointers or something, and it's easy to mix them up and get all kinds of strange things to happen. So as a general rule of thumb, people who program in C run across a lot of accidental complexities. Even C++, if you're not careful, you can run into these things. And that's why it's really important, if you program in these languages, to get in the habit of using tools like Valgrind or Purify or other things to check for common mistakes. Not a guarantee of success by any means, but it'll at least sand off or file down some of those sharp edges. And of course, pthreads doesn't work on Windows, so you're already stuck. Other C-based APIs have the same kinds of problems. Another set of problems we run into is tricky parts with debugging. So when something has gone wrong with your program, you've got to figure out how to make it work right. First thing you have to do is figure out what's wrong. So back in the bad old days, back in the medieval times, if people were afflicted with various kinds of ailments, what they would do is they would apply the treffing technique, where they would drill a hole in your head to let the evil spirits out, right? So that was obviously a very limited tool. We have much better tools, things like CAT scans or MRIs or something like that. But that's a very limited tool to try to figure out what's going on inside of yourself or your program. With respect to debugging tools, one of the problems you have with multi-threads is the minute you start running your threaded programs in a debugger, oftentimes the scheduling order or the execution time may start to change. So threads that ran concurrently before may be now artificially serialized due to the fact that you're running them in the debugger. And you may be stepping through a certain thread which may not be at the normal rate that the thread would run if it wasn't being stepped through with the debugger. So any bugs that you have in your program due to subtle timing conditions are really hard to find. They're subtle and pernicious, as we like to say. And that makes them tedious and error-prone to try to track down. So timing issues become tricky. Another big problem you end up with is the fact that in concurrent programs, if you're not really careful and you don't lock your data properly, you can end up with what's called race conditions, where different threads of control crash into the data at the most inopportune time and change it in various inconsistent ways, which is really, really, really annoying. Java gives you a bunch of ways to help with that, but the problem still exists if you're not really careful in how you use it. Once again, strongly recommend you take a look at various static and dynamic analysis tools that will help you to detect these kinds of problems. It's hard enough if you wrote the code to figure out what's going wrong from a debugging point of view. If you inherit code from someone else who wrote it, and they have lots of threads, and they weren't really careful, all kinds of strange things will happen, and it's very tough to debug because the tools are not as robust as we might like. So those are the accidental complexities. Sometimes you can get around these accidental complexities by moving to a new language, moving to a new environment, buying or learning to use a better set of tools. So that's what makes them accidental complexities. There's also inherent or so-called essential complexities. These are the complexities that are often hard to make totally go away, even if you program with a different language or even if you use better tools, because they're just part of what makes it hard to do certain things. It's the rocket science of programming. It's also why people who are really good at concurrent and networked and synchronized software development are in such high demand, because it's a very hard thing to do. So let's talk about some of the complexities. One of the complexities is synchronization, which is the application of mechanisms to ensure that two or more concurrently executing threads don't try to execute the same piece of code accessing the same data at the same time, so without being protected. So there are various locking mechanisms like mutexes or reader-writer locks or semaphores or so on that can be used to try to synchronize or coordinate access to things that are shared. So it's very important to have that sharing property right. Some good descriptions about this at Wikipedia you might want to take a look at. Another related but different concept is the concept of scheduling, and that's the method by which threads or processes or data flows or so on are given access to shared system resources. So the example here, of course, is trying to land airplanes at an airport, right? There's a shared resource. It's called the runway. And talk about, race conditions. You do not want multiple airplanes trying to land on the same runway at the same time. All kinds of bad things happen. So the same thing is true in your computer. You want to make sure that things get scheduled to run at the right times. You also want to make sure often that everybody gets a chance to eventually make some progress. Otherwise, they'll get starved out. That's one of the differences, by the way, between real-time systems and non-real-time systems. In a non-real-time system, fairness is important. You want everybody to get a chance to get a turn. So people often use scheduling disciplines like round robin, where you take turns and each gets a little 200 millisecond time slice or whatnot to do their thing. There's also real-time systems where, the heck with fairness, I want to get the most important thing done first. And so in that case, you do things where priority takes precedence over fairness. And as long as there's somebody of higher priority to get the job that needs to have a job done, they get a chance to run, even if they preempt other things that never run. Okay, so there's more stuff about scheduling. And then another inherent complexity of concurrent software is deadlock, which is basically a situation where two or more competing actions are waiting each other to finish. Basically, it's mutual waiting or mutual dependency, and thus neither of them can actually get the job done. So basically, if you have a couple of locks and a couple of threads, you have to be very careful the order in which you try to acquire the locks, because if you don't, one thread will acquire one lock and try to get the other one. The other thread will acquire the other lock and try to get the other one, and they deadlock. And it turns out that trying to write deadlock-free software in many applications and many languages is rather tricky. And there's a lot of techniques you can learn to address those things. There's patterns, there's algorithms, there's tools, but it takes a bit of thinking. If you have a chance to take some of the advanced operating systems courses at the graduate level, you'll often study various algorithms for deadlock detection. Okay, so to summarize this discussion, concurrent software helps to leverage advances in hardware technology. We've got all this hardware, we might as well find a way to take advantage of it. And of course, the reason for doing this ultimately is to get better performance, either better real performance or better perceived performance. And we have to be able to deal with the fact that some of the complexities we run into have to do with limitations from the tools that we use. They're too primitive. Other limitations really have to do with fundamental challenges of the domain. For all those situations, patterns, frameworks, reuse, middleware, knowledge of data structures and algorithms, they're all very important things to be able to address the challenges in that space. Okay, any questions? So that just provides kind of a background of concurrency. You may have known some of this before, but I don't know if there's other classes at Vanderbilt that really go into this until you get to the 281 course, so I wanted to do a recap. Okay, next topic has to do with understanding the first layer of things for how you program concurrent Java applications. And we're going to come at this from a bunch of different directions. I'm going to start by talking about how you program concurrent applications, and then we're going to kind of we're going to look underneath the hood and see sort of how it works. And then next time, we're going to talk about various synchronization mechanisms. We're going to talk about some of the other dimensions of concurrency. So the first point is that Java implements many of the classes that you would come to know and love if you were just a Java programmer. So if you take a look at the Java website at Oracle, let's go ahead and see if we can do that. So you'll see that there's a whole nice tutorial there about concurrency. And if you click your way through there, you will learn about processes and threads in Java. And they'll show you how to program these things and so on and so forth. So not a bad thing to know. Some of you may know this already, but again, I'm not sure we really cover it in a systematic way here at Vanderbilt. So I'll cover a little bit of this stuff now. From a conceptual point of view, what you have are a number of processes in Android. These are Linux processes, although you as a Java application developer don't really see the Linux-ness of it unless you drop down to lower layer programming abstractions like the NDK part. And they basically allow different threads that are running inside of those processes to communicate to each other either by sharing memory or sharing objects or by passing messages to each other. And there's lots of different variations on a theme that you'll run into in Android to do this. Most of the stuff that's part of Java concurrency is supported, but you'll find that there's a certain number of idioms in Android that are more important. From an implementation view, and this is important, it always shows up as a quiz question, each Java thread has a program counter and a stack. Those are unique things, and we'll look in a minute when I get done with this overview. We'll look more at how it works under the hood, and you'll see how Java threads are actually implemented under the hood by Linux threads, which are themselves implemented under the hood by kernel level resources that are cloned. So these are the unique characteristics, and then there are also some other things that are shared. So the static data, the heap data, those things are shared within a process. Not across processes, but within a process. There's also some other Android stuff that you can do for shared memory we'll talk about much later in the course. For right now, we're going to pretend that doesn't exist for this discussion. So heap and the static areas are shared across threads within a process. The program counter, the stack, other thread-specific kinds of things are unique for each thread. And so here you can see the abstractions, right? We've got the processes, which can have one or more threads. A thread is a stack of functions, and these things all run on top of different cores. So that's my symbology for multi-core, multiple Apple cores. A non-copyrighted image, so I could use it without having to worry about royalties. There's some really nice discussion about all this stuff here at the Android website. Let's see if we can go ahead and bring that up. And what you'll learn there, it's actually kind of interesting. So if you just read the Java threading material, you'll see some perspective on processes and threads. If you start reading about Android, you'll see that there's a lot more stuff going on that's very specific to Android. So you'll see how they do descriptions of what goes into a process through the manifest file. You can define certain services, for example, run in their own process. We'll get a chance to play around that later in the course. There's a life cycle for processes. There's foreground processes, visible processes, service processes, background processes, lots of different kinds of processes that are used by different parts of the Android system. And then there's a whole bunch of stuff about threads. And this is the part about worker threads. We saw some examples of worker threads a minute ago. We'll look at more. And then there's async tasks. So there's lots and lots and lots of stuff that you should take a look at in order to understand how Android adds value added to what you get out of the box with Java. Oops, come back over here, pop back up to this view. So let's take a look at how you actually go ahead and program threads in Android. Now I'm going to give you just a simple perspective. There's obviously a lot more to thread programming than we're going to show here. This is just a way to get a good sense of what's actually going on. Some of you may already know this stuff, but there's some interesting nuances we'll discuss. So obviously in Java you have to be able to give some code to run in a thread of control, and ultimately this code starts from or is encompassed by a hook method called run. And so the question is, how does run get run? So there's a couple different ways to go here. One thing you can do is you can extend the thread class. So java.lang.thread, that's a built-in class. And if you say, class myThread extends thread, you can then fill in your method to do the work in run, or you can have run delegate to other methods you might write. And then to make this all work, you go ahead and say, make me a new thread object or myThread object, and start this guy up, and away he goes. So this is a particular example of using a named class called myThread in order to be able to go ahead and do this. Another way you can do this, which is actually pretty common, is to implement the runnable interface. So you can see before we inherited from thread, another way to do it is to implement runnable. So in this particular case, we have myRunnable, which implements runnable, and then we go ahead and do whatever we want to do here. And we use our little UML notation to show, this particular notation shows implements, this notation shows inherits. And then down here we make a new runnable, and then we say new thread dot start, but we give it the runnable object to run. And so we're using a named implementation of a runnable. So in this case, it's my runnable. That's another way of doing a thread invocation. Yet another way to do this is to use an anonymous class or an inner class. This is a very, very common thing. You'll see this used all the time in Android. The example I showed before, where we were doing the image download, used exactly this technique. So what we do here is we go ahead and we say new thread, new runnable, and notice we don't name it. It's not a named runnable. And then we go ahead and just create an anonymous inner class that has run method filled in, and then we tell this new thread to go ahead and start itself. That's a nice anonymous way to do things. So those are sort of three common ways. You'd be surprised the extent to which the anonymous approaches are used in Android, especially if you're doing stuff that's being called in response to a button click. Very, very common technique, used a lot. OK, so after start gets called, some interesting things happen. So here's an example that kind of shows how this works. And then we'll look at a more subtle view of this in a minute. So let's say that you have some kind of activity. So it gets created, and it turns around and it creates a new thread, creates a new my thread. And then we say start. And what that goes ahead and does is it goes ahead and it spawns a thread of control and its own stack. And we'll look at how that works later, and I'll walk you through the code that's part of Android that does all this stuff behind the scenes. And so what that does is now we've got sort of two things that can run concurrently. The original code, which called start, can keep running. And then the code that was started will run when its run method is called. So those things, especially on a multi-core processor, really, in fact, could execute in parallel. Now, there are various ways for things to happen after this point. But the bottom line is, if you want code to run, you have to put it in the run method or a method that's called from the run method. Now, as long as run hasn't returned, the thread will be active. And you have to be a little careful with the use of the word active here. It could actually be suspended for some period of time as the scheduler suspends and resumes it, which I think I say here, pauses and resumes it. So what that means is, if you want to have a thread that runs forever, where forever obviously is bounded by certain things, then you need to put a loop somewhere that says, while true, or for, open paren, semicolon, close paren. Just keep looping until I shut you down some other way. We'll talk about how to stop threads later. A little tricky thing to do in Java. So once things are up and running, then they're running concurrently. The Android scheduler can come along and say, or the Linux scheduler really could come along and say, I'd like you to stop running, please, because I need something else to take its turn. But essentially, you're logically active until you return. When you can see here, when run completes, when you fall off the end of run, then that thread goes away, and depending on a variety of things, that's either the end of it, or it's also possible for the calling thread, or some other thread for that matter, to join with the result of a thread that was created before. So if you want to, and your thread returns a result, there are ways of being able to pick that result up by joining with it. That doesn't always occur, but it's possible. So the basic point here is that there are certain mechanisms that are part of Android that are just garden variety Java kinds of stuff. And so if you know how to program Java threads, then you should have very little trouble using Android. The tricky part is to know when to use those mechanisms. And that is indeed tricky, because you'll see that in Android you really don't use a lot of these things quite the same way you would use in a desktop or a server application for various reasons. OK, so the next topic here is to kind of peek a little bit more under the hood and look at how this stuff is actually implemented. And if you look at the way that threads are implemented in Android, and we're going to look at those in a minute in a bit of detail, you'll see that there's certain layers that are involved. So of course, there's the core Java libraries. These guys, the core libraries like Java Lang Thread, they're involved. But there's also other stuff involved. For example, there are some things that are part of the Dalvik virtual machine that are involved in implementing a thread. There are parts of things that are a part of the libc library, like the pthreads library, that are involved in dealing with threads. And then underneath the hood, of course, way down here in the bottom of the kernel somewhere, there's the low-level operating system internals that are dealing with the threads. And that, of course, is what's really doing the heavy lifting to map those things down to the underlying processor cores and so on. So the point is there's a lot of different moving parts here. Before we talk about the moving parts, though, let's just spend a little bit more time talking about the various states that a thread can be in and how it gets into those states and how it transitions between those states. So the first thing you do, of course, is you create a thread, which is almost always done by saying new, whatever the subclass is, my thread or my runnable or something like that. And so now you have a thread object. But at that point, there's no real major resource allocation being done. You just have the object in your hand or in your virtual machine memory. So at some point, you'll say my thread or my runnable dot start. And that's going to go ahead and kick things off. At that point, for reasons we'll look at in a minute, you'll see that there really are resources allocated by the operating system. Stacks are allocated and so on. Or a stack is allocated, registers are allocated, other resources are allocated and so on. At that point, once the thread is started, it's now runnable, which means that when the operating system scheduler decides this thread, it's this thread's turn to run, and that could be based on a variety of different characteristics, like the time slice, its time slice is ready to go, or if it's a real-time thread, it may have preference by some other means. But the thread scheduler says, okay, now you can run. But when something's runnable, it's actually not running, it's just ready to run. It's kind of like a pitcher warming up in the bullpen, getting ready to go out and pitch. So a pitcher warming up in the bullpen is not actually pitching to the opposing team, but the pitcher's getting warmed up. Once the scheduler decides, aha, this is your chance to shine, then it goes ahead and lets the actual runnable thread become a running thread, and now it's doing its thing, and it'll keep doing its thing until one of several things happen. One thing that may happen is if it's just doing, say, a long-running computation, like an algorithm that is just looping and consuming memory, when its time slices up, which typically comes every 100 or 200 milliseconds or so, it may say, okay, it's your time, go ahead or do your thing. Actually, I think it goes faster than that. I think it's probably every 10 milliseconds or so. But every period of time, it's given a chance to run. And once it's done, it could be suspended. There could be some other reasons why a thread would give up control of the processor. For example, one thing it might do is the thread might say, I'm going to go to sleep for whatever reason. Now, for those of you who are more advanced in concurrency, you probably know that sleeping is actually a fairly rare thing to do. Sleeping is a very tricky thing, because how long do you sleep? And there's a whole bunch of complexities dealing with that. But it's possible to sleep a thread. And if a thread is sleeping, it goes into the sleeping state until it's done sleeping, at which point it goes back to the runnable state. So now it's capable of being rescheduled. When the sleep period elapses, that doesn't mean the thread automatically runs. It just means it's eligible to run again. Another thing you can do from the running state is try to acquire a lock of some kind. So you might have a semaphore, or you might have a mutex, or you might have a reader's writer lock, you might have a condition variable or something. And when you go ahead and wait on that lock, then you're going to be your thread that does the call will be put into the waiting state, and that'll give other threads a chance to run. And we'll talk more about that probably next class when we talk about the monitor object pattern, which is a really important pattern in the context of Android concurrency. So while you're waiting, at some point someone can notify you or somehow release you from your approach, and so now you would no longer be waiting, you would now be back to being runnable again. Another thing you might try to do is you might end up blocking because you're attempting to access some kind of guarded resource. And there's a variety of different things that you might do there. You might be blocking on I/O operations. For example, you might be trying to read from a file or read from a network connection, and they don't have any data there at this point, so you just kind of block for that. And then at some point, when you're done, you go ahead and terminate. And there's various ways to terminate. You can shut yourself down. You can fall off the end of run. Someone can come along and nudge you to try to get you to shut yourself down. There's a couple different techniques. Nolan?
Is blocking ever intentional?
Oh yeah, sure. Like if you do a read. Yeah. Good example would be reading. Okay. Any questions about the state machine for Java. Now, part of the issue here is this is mostly under the hood. You most of the time don't really need to know about this stuff as an application developer, although there are situations where you're debugging your code where you may be poking around in the Java virtual machine or other parts of the system, and you're come across these data structures that are telling you something about the state of your thread, and it may be in one of these states, blocked, waiting, and so on. And so it's useful to understand these things, because you'll find yourself having a program that's not responsive, and you may have to go into the debugger and do a backtrace and see, aha, I'm waiting on something. Why am I waiting here? What's the reason it's not getting what I want? And so on. So it's good to have a working understanding of how these different states occur. Okay, so now let's spend a little time talking about what happens when you start a thread. And this is actually kind of cool. So when you start a thread, a whole bunch of things take place under the hood. So you have a thread, my thread, you say my thread.start. Well, what that does is that ends up calling thread.start, which is a Java method. And we can go and take a look at the source code for this thing. I'm not going to belabor it, but I think it's kind of fun to take a look at this stuff. So here's the ice cream sandwich version of Android. And here's thread.java. So this is the implementation of the thread class. And so if we search for start, here it is. There's start. So you can see start's a pretty short method. And all it does is it goes and it calls VM, virtual machine thread, .create, and it passes in the default stack size. All right, so that's start. So that calls vmthread.create. Okay, let's go take a look at vmthread.create. So vmthread.create is in this file. And that's kind of interesting. Look at that. That's what's called, if you can see it, it's a little hard to see. Let me make it easier to see. That's a so-called native method. What does it mean in Android when something is a native method? Well, one of the things it typically means is it's not implemented in Java. It's typically implemented in C or C++. And so you're not going to find that code lurking around in that file, which is a Java file. All right, so let's go back over here. And the next thing that happens is this native method is actually implemented inside of the Dalvik source code. So let's go take a look at that. So we go over here. So this is Dalvik. Dalvik is the virtual machine that comes with Android. And as part of Dalvik, there is a native directory, which is where all the various native files are. And inside of this thing, there is a function called dalvik_java_lang_vmthread_create. Kind of a mouthful. And you can see here it passes in a bunch of arguments that are expected by the so-called Java native interface, the JNI. And what happens here is we take these things, which are just void pointer-like stuff, they're pointers, and then we cast them back to what we want them to be and extract out the various things we want. And then we go ahead and we say DVM, for Dalvik Virtual Machine, create interpreter thread. So that's a call actually inside the virtual machine. So now we're inside the virtual machine at that point. So let's go take a look and see where that guy lurks. So that's in Dalvik VM thread.cpp. And let's see where that guy is. That's right, create. There we go. So here's create interpreter thread. And you can see this does a whole bunch of different things. The long and the short of it is it goes down here and it calls the very famous pthread create method. If you recall, pthread create was that method we looked at about half an hour ago that I showed you that was that nasty C code that was very low level, where it was all kinds of accidental complexity. So that eventually shows up. If you poke around long enough in the call chain here, you'll find that code, except it's been abstracted away from you by all these layers of abstraction that's in Android. So pthread is going to get called. Pthread create gets called. And that's actually over here. So it's in this library called Bionic. Sounds like the Six Million Dollar Man or something like that. People don't even know what that is probably, but it was a great TV show in the 70s. And if we poke around in here, we're going to see pthread create. Here it is. And at this point, now we're into very low-level operating system library call stuff. And I'm not going to trace it any further than this, but if you were really gung-ho and wanted to feel a lot of pain, you would go look inside the kernel source, and you would find that there's this thing called pthread clone, which creates a copy of the process. It's lightweight, optimized for threading, blah, 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 all kinds of cool stuff. So that's very, very low-level code. We're not going to get quite that low, but you're welcome to follow that. That code eventually calls back to this thing called interp thread start, and that's back in thread.cpp. I won't go back and look there. That calls dvm call method, and then finally that calls back to the run hook that you defined in your class originally. So it's almost sort of like a Mobius strip. You start at one end and you follow it around and you come back to where you started, right? So we started out calling start on my thread. We went through a whole bunch of different layers of calls through the Java class library implementation, through the Dalvik virtual machine implementation, down into pthreads, down into the kernel, and then back out to the Dalvik virtual machine, and then finally a call back to the hook method on your code, all just to get run to run. And somewhere along the way, a stack was created. When pthread create is called, it actually makes a stack. So up to that point, there's really nothing allocated that takes up real virtual memory. But when pthread create is called, now you got a stack. So that's basically how things are started. Kind of cool. It's also fun just to know how to poke around in all the source code to Android. And that's one of the great things about it being open source. You can see a lot of the stuff and how it works. OK, just a couple more things and we'll wrap up. Other than returning from run, there's no safe way to stop a thread. There are various sort of non-portable ways and very tricky and dangerous ways to do it, but they're not recommended. So you have a couple of different ways to do this. You have to sort of collaborate with you, the one who wants to stop a thread, has to collaborate with the thread to get it to stop. So one way to do this is to send an interrupt method call to a running thread, or to a thread that has been started. And when you send an interrupt call, then periodically your thread needs to check to see if it's been interrupted. And if it has been interrupted, it goes ahead and throws the interrupted exception. Certain operations, like blocking read calls, the various synchronization calls like wait or join or sleep, those are automatically interrupted if a thread is interrupted. They're automatically unblocked and they return, and exceptions are thrown. The interrupted exception is thrown. But if you're just sitting there in a tight loop, just spinning, computing some, the value of pi to some ridiculously long decimal point, you do not get interrupted. So you have to stop periodically and check to see if you've been interrupted if you're doing compute-bound work. There's some more descriptions about how this works here. Another way to stop threads is to use the stop flag approach. This is a bit more tricky because you really have to make sure that you write code that does the right thing. So you use a stop flag, add some kind of Boolean flag to your class that you're trying to be stoppable, and initially set running to true. And while you're running, then you're fine, but you have to continually check to see if you're still running. And you may not want to just pull it, but you may want to sleep or block or do something and then periodically check that. Yeah?
You probably want to make the flag volatile too.
Yeah, you should probably make it volatile so that it will be propagated properly. Yeah, that's a good point. So this is another technique you can use. If it's up to me, I'd probably prefer to go with the interrupted approach because that has a bit better integration into what's going on in Android, and it'll unblock certain calls. But this is another way to go. OK, so to summarize this section, the Android threads are implemented by various methods and functions that appear up and down through the stack. And one thing to remember is that even though threads look really simple, the actual implementation is not free. So you start spawning lots and lots of threads, and there's actually going to be a memory hit. So that's one reason we're going to talk later about other mechanisms of reducing the number of threads by using other kinds of patterns at your disposal in order to try to get a control over the total resource utilization. OK, any questions about any of that?